We have started recording.
All right. So another thing that we were hoping is that depending on who comes, we would like for those people who are here to participate if they want. Like just ask questions or introduce themselves or whatever. If they don't feel comfortable, that's all right too. But definitely everybody who is here should feel invited, to participate, just to ask questions or comment on things.
Yes.
Yeah, actually, it's good to ask questions because since I'm not really spend too much time on preparation, it would be nice to hear some questions.
Great. All right, so go ahead.
Okay, so I can start, yeah?
No. Hang on just a second. So listen, I know that you share the screen, but let me share the screen again, and then we're going to start again. So I'm going to do this now. Hang on, let me find this Zoom. So you are sharing the screen, but please let me take the screen away a little bit from you, and then we'll give it back to you. So I cannot. I can't. Could you let the screen? I want to show something, and then we'll. Could you unshare the screen?
Share again.
Yeah. So okay. All right. So what am I showing? Am I showing the slide with you?
Yes.
Good. So what I wanted to say that today is December 13th, it's Tuesday, and this is our Quantum Information Science and Engineering Student Journal Club. Arpan is the host. This is our intended guest speaker, but she is not available today. And so instead we got Dr. Demid Sychev, who is a postdoc at Purdue University Quantum Science and Engineering Institute, who has a joint appointment between the groups of Sychev and Yong Chen. And with this introduction, let's just hear from Demid things that he's studying over there and that we could maybe hook into in some sense and participate and collaborate.
Thanks for introduction.
Okay.
Can you see my slides?
Yes.
Okay. Yeah. So I'll start a little bit from far. In general, the quantum information science probably one of the most interesting fields currently and one of the most popular in scientific community. So it is the goal in this field is to use quantum laws of quantum mechanics for some data processing or for computation or for any other task, and to make some advantage of it. And for example, it is well known Shor's algorithm, probably one of the most And the measure seen in quantum information science is a qubit. Compared to classical logical 0 or 1, qubit is a unit of information which can be not only in 0 or 1, but also in superposition, which is completely different from classical approaches. So, and it gives some advantages. So it was shown that such an approach based on qubits can lead to advantages in quantum speed of quantum computation. For example, Shor's algorithm has been shown that the complex number can be decomposed into simple numbers far more faster compared to classical computational approaches. So there are many different approaches how to implement such a system in physically. What you need a qubit, something which can be in a superposition of two levels. So and you can use for this single atoms, ions, or any other two-level system, and which you can manipulate. And another approach is based on photons. Photons also can be in a superposition of different states. And compared to other platforms, photons have some advantages. For example, they are not decoherent, and they are massless, and they can travel with the speed of light, which makes them the only platform suitable for quantum communication and for transferring quantum data through the space. So there are several examples of real systems which already has been implemented based on photons. On the right side, you can see recent experiments on so-called boson sampling, where some simple, not simple, but specific tasks were solved much faster, which cannot be achieved with classical computers. So it was achieved in a group of Jae and Pham in Science in 2020, and another approach was realized by Xanadu. Instead of working in parallel with qubits, they implemented so-called time loops and encoded information in time. And another example of how photons can be used for quantum applications is quantum communication, which is shown on the left, where it was realized a link between several cities through the optical beam. And so any system, any quantum optical system, in principle, you can consider it as a n-photon n-mode interferometer, which has n sources of photons and the same number of single photon detectors. And using different phase shifters and beam splitters, you can accommodate this system for the task you want to solve. So the example on the right, you can see two different approaches. One is on top, on table, just about optics, and you see it's a very huge system, which actually I showed on the previous slide, but here just you can pay attention how much space it takes. And that's why it's very important to use approaches which allows you to build scalable systems, many, like ideally something compared to electronics where you can manipulate with millions and thousands of qubits. And the only approach which you can use it for this, probably the most well-known is on-chip based photonics. So on the bottom, you can see example of such a schematic. So yeah, another problem that you must use high quality single photon sources for such a system. If you're not using it, it will not work. So the most common approach is based on spontaneous parametric down conversion with nonlinear optics, which is based on generating of pairs of photons in nonlinear medium. Another example is based on single photon emitters like atoms or solid state emitters. It's basically a two-level system which you excite, and when it's relaxed, you can see it can emit a photon. So the second approach is more has some advantages. For example, it can be in principle deterministic. Deterministic means that if you launch the system, it generates a photon. But with spontaneous parametric down conversion, it's a probabilistic process. It means that not every time you have photons on its output. And this is one of their main problem for scalability, because if you have like some number of single photon sources, and if they work only with some probability, if you have millions of such a photons, of such sources, then the probability of generating all million photons will be negligibly small, so that the rate of getting results in your scheme will be almost zero. So another problem is that the quality of photons should be good. What does it mean? It means that if you have two photons and you overlap them on a beam splitter, and they should show Hongo-Mandel effect, which means that both photons goes either in one or another detector, but not simultaneously in both photons. This happens because of the interference between probabilities, amplitude of probabilities, and this is purely quantum effect. And if you do not have indistinguishable, so-called indistinguishable single photons, you will not see such an effect. And here you see an example what you will see if your photons are distinguishable. So yeah, the picture, the plot which is shown here demonstrates the effect of Hongo-Mandel. You send several pulses, and on the x-axis it is a delay between two pulses. And when your two pulses are completely overlapped in time, you see zero coincidence, which means that you observe Hongo-Mandel effect. And here you can see that it drops almost to zero, meaning that the quality of photons is pretty good. But with solid state emitters, there is a problem that because they interact with media and interact with many with environments, they're largely affected by temperature, by phonons, and many other different things, which makes them to fluctuate. And this fluctuation can be very big. You can see the spectra of nitrogen vacancy center in diamond, which probably one of the most well-known emitter. And it's very broad. It's very broad, so that if you take two photons from two different sources, every time you send a pulse, each of them will generate slightly different frequency, or even not slightly different frequency. And of course, photons of different frequency will not produce any interference. And that's why at room temperature, from many solid state emitters, for example, it's impossible to see such an effect. Hypothetically, it's possible to cut some narrow line of the spectra, so that only the photons with a certain frequency will pass through this. And in this case, you can see interference, but the problem that you will lose the rest of the photons, and the probability of getting coincidence will be low, so that efficiency, overall efficiency of the system will be low. So both parameters, indistinguishability and efficiency, are very important for scalability. So there are several approaches how to solve it. First is to decrease the temperature. So decreasing the temperature is probably the most common approach, but it's not always accessible, because it requires cryostat and some complex system. So, and not everywhere it can be implemented. For example, if you are somewhere in space or whatever, it may not work. And the third approach I said already something about spectral filtering. It's just too slow. That the third approach is decreasing and make indistinguishable photons through partial effect. So partial effect, it is effect which occurs in the cavities. If you place your emitter inside the cavity, you will see enhancement of your rate according to the formula in the corner. So whereas Q, it's a Q factor, it's roughly saying how long the photon lives inside the cavity, and V is the mode volume of the light of this cavity. So if you take a cavity with a very small volume, you will see a very huge partial factor. Or if you take very high Q factor, you will also see very huge partial factor. So it will affect the lifetime of the emitter. So why it is important? Because because the figure of merit of indistinguishability of photons can roughly be estimated through this relation on the screen, where tau is the lifetime of a photon and delta omega is the width of the spectra. So you, in principle, can have either very short photons in time, so that spectra is very wide, or you can have very narrow spectra but very long time of your photon. And if you overlap them, in both cases, you will see interference if this ratio equals to 1. If it's much higher than 1, then it doesn't matter. Then it's not indistinguishable single photon source. So, and there are several approaches how to do this. So you can see 3 cases. First case is just in the center. Second case, if you place this in the center in the photonic cavity, you have a Pascal factor from 10 to 100. And the final one for plasmonic cavities. Plasmonic cavities, they are much smaller, and the mode volume there is around several tenths of nanometers, which cannot be achieved with photonic cavities, for example, because it is limited by the diffraction and wavelength of your photon. But with plasmonic cavity, you do not have such a limitation, and in principle, you can enhance it even more. And that's one of our approaches. That's one of the things we are working here in the lab. So here as an example, we, for example, take a nanodiamond within the center and place it between the nanocube. The side of the cube is around 100 nanometers, and we put it on a substrate epitaxial silver. And because of the gap plasmon, the volume between these 2 pieces of metal is very small, and the light is confined, and the mode volume is small, and you can have reach very high Pascal factor. And high Pascal factor means that the photons coming out from the single photon source are short in time, and it helps a lot to generating of indistinguishable single photons. Yeah. So other approaches, but probably it's still not enough. I mean, even with such a plasmonic cavity, it is still not enough to generate good photons at room temperature. But you can slightly increase their operational temperature for your system if you apply any kind of cavity. Yeah, and parametric down conversion works all the time, even at room temperature, because it's in different kind of process, which is much faster compared to any decoherence processes. That's why, in principle, it doesn't have such a limitation. So, as I said before, another interesting problem which should be solved is on-chip integration. And this is one of our projects which we are working on, where we try to do some small steps for integrated photonics. So basically, we are trying to fabricate waveguides, silicon nitride waveguides, with single photon sources inside, and this approach potentially possesses high scalability, and so recently we even were able to find some emitters inside this silicon nitride platform. So because it's a separate problem how to build a cavity, how to fabricate a waveguide and how to connect it to your single photon sources. but it appeared that in silicon nitride, both things can be realized very easily, because you can fabricate single photon sources just by annealing of silicon nitride. And this first experiment of coupling this emitter to waveguide. So here you can see the example, and you see that it shows some single photon features, such as G2. So G2 means that if you send a single photon to a beam splitter and split it into two passes, when your photon is going to such a system, it cannot go into two detectors simultaneously because it's only single photon. Yes, you cannot split it, and you can see deep in time correlation in this case. And this is a signature of a single photon. And usually a good single photon sources typically around something below like 0.2, but in our case it's exactly 0.2, but it's not so bad. What we probably in future will try to implement is shown on this right slide. We want to merge emitters with plasmonics with silicon nitride waveguides, and try to implement a system which shown here. Of course, we have only two separate experiments. One is just about the silver nanotubes, which is very hard to couple to waveguides. And on the other side, we have some silicon nitride waveguides, but that probably requires a lot of more steps to realize. Yeah, I think that's all what I wanted to say, and I'll be happy to answer your questions. I think, yeah, it would be nicer.
Thank you. That was wonderful. And now, if anybody has any questions, that would be a good time to ask them.
I had a question.
Mm-hmm.
When the pulses of light come out in short durations, right? So you're trying to distinguish each part of the emission. Would it be fair to classify that as a pulse?
Yes, in principle, you can walk even. Finally, after all, this system, this photonics, will walk as a sequence of pulses. So you have a laser with some pulses, and you excite your two-level system, and the time which it takes this two-level system to decay, it's the lifetime of a photon.
Okay.
And yeah. But some of the effects you can see even without pulses with continuous wave laser as well.
Okay. Okay. You mentioned that you require a certain temperature to do this.
Yeah, for single photon emitters, the problem because of the environment, the spectrum is broad. And such photons do not produce interference, and that's why you cannot use them for optical circuitry. And you have to either decrease the temperature or apply Parcel factor. But Parcel factor is not enough to see anything even at room temperature. That's why anyway you have to decrease it. Yeah. And usually people are combining both approaches. There are a lot of works at low temperatures with photonic cavities, for example.
Okay. Now I wanted to get a sense of the range of temperatures we are looking at.
For single photon emitters, it's usually something below 10K. Maybe in some rare cases you can go higher, but this more standard one. Well, but as I said, parametric Dunn conversion, for example, nonlinear optics doesn't require any low temperatures. So here, in both of these works, like actually on the right, examples of quantum machines which demonstrated an advantage, they were built on a parametric Dunn conversion, spontaneous parametric Dunn conversion, which is probabilistic process, but it doesn't depend on the temperature and produces high quality photons. But this is the problem why probably this approach will not go to higher scalability because of the probability of generating single photons. To the high scalability. Yeah.
I also would like to ask you something about this. Would you say that this is physics research, like 100% physics advanced research? Or would you say it's interdisciplinary?
Yeah, this this is more, yes, like we are trying to find the way of trying to ways to solve a particular problem. And this is more, I would say, engineering, but of course relying too much on physics because actually there are many effects which affect this photon quality. And of course we at some point will have to learn a lot about it and improve it. And
yeah,
so
so it's engineering and physics. It's not just physics, and it's engineering and physics. So I think that, you know, in general, quantum technology has been with us for a long time. For example, quantum sensing has been around for 50 or more years with significant results, but people have started being so interested in this, mostly in recent times, on account that these companies now exist. We have like 60 companies worldwide making quantum computers. I guess they work routinely around 100 qubits. And when they talk to investors, they say, by the end of the decade, we're going to have 1 million qubits, particularly the photonic people like Xanadu or maybe PsiQuantum. So from this point of view, students, undergraduates, come and say, well, we want to study this. When can we see such a thing? So suppose they say, okay, we can put up with the math, we like it, we learn it, we understand the algorithms. Where exactly do we communicate with the hardware? So my question really at this stage is, what part of what you told us about, or maybe what you might tell us about, do you think could be scaled down so that a computer science undergraduate could absorb it? So this, I know this is a hard question. So the reason I'm asking this is not just because of the CQT that exists between Purdue IU, Notre Dame, and IUPUI, but we also have a master's in quantum information science, which is on purpose aimed at students that have finished an undergraduate degree in STEM, but not in physics. So my question then is, what do you think can be offered to non-physics students while they are undergraduates for them to start interacting with quantum hardware?
Yeah, so in this regard, I think this photons are probably the best platform, because many of the toy things can be realized with photons without cryostats even, and they give a good example of how quantum mechanics works and what the effector observes. And of course, because it relies too much on physics, it's very important to understand the limitations of the system, because in principle, as it was shown, like quantum algorithms are better for some applications and faster. But at the same time, we do not have currently machines which are capable of producing this advantage in a standard way. And that probably will require understanding of limitations and like from both sides, what algorithms can do and what physically quantum machines can do. And like overlapping between these two will produce this advantage, I would say.
The impact.
Yeah. So I think that's how I see this.
I see.
That of course it's very important to understand the physics, and the best way to understand it is probably work with photonics quantum machines, for example, which are much easier to like put on a table and do something. And after this, you try to understand how to implement some algorithms.
Yeah. So basically, the first question, I was going to say something and I completely lost because I thought of something else. Okay, the one thing that I wanted to clarify is that everything you showed us today is stuff that you've put together and verified, right? Everything you talked about is you've built, and then you've made sure that the results are the way you communicated them to us, right? So this is not theoretical; it's experimental and engineering.
Yes.
Okay. So we cannot go around physics. Okay, we can replace the physics with some mathematics, with some other rules, and once they understand, eventually, when they have to build something, they have to talk about the physics and they have to respect the physics and so on. But if there is a way for us to bring the material to undergraduates, my question now is, what do you think can be done to bring it at the level, or what kind of material could be brought at the level of high school? Because we are also interested in creating an outreach program for high school teachers first, and then high school students. So first, let me ask you this: how did you get interested in physics, and did you do quantum physics in high school? And if so, how early?
In my case, I wasn't very well familiar with quantum information science when I was graduating and finishing my undergraduate school, but I was familiar with many quantum mechanics related stuff like superconductivity, semiconductors, very classical physics. So, but it's a little bit not the same as working with qubits and understanding the qubits and photons. And actually, I got familiar with it only when I started doing my PhD. Yeah, but I agree that when earlier you start, more you can have time to do something interesting and useful and opportunities. Yeah, and I agree that simple photonic systems, simple experiments, which can bring some understanding to students, is very beneficial for this process.
Right. So over here, things are different at the level of high school on account that people don't want to teach what doesn't count. And so quantum is not in any way required. We went to Canada over there in Waterloo last month, and they have a different system over there. There was a workshop called Schrodinger's class, and the purpose was to provide materials to the high school teachers in Ontario, but also all throughout Canada. They had people from 5 countries, different countries. And the idea is that in different countries, Germany, I think, was there, in different countries, the syllabus is different. And over there, they have it in the textbook, whereas here it's a little bit disorganized and decentralized. And so it's not clear to me how exactly we could go to high school, although we have started doing this, and what can we tell them at the high school level? I suspect just diagrams. But at the level of undergraduates, you say that perhaps photonics would be the way to go to try to build simple systems?
Yeah, it's got through experiment. Well, actually, I'm relying on my experiment, my experience, because like everything is much easier to see how it works when you do something with your hands. But it's probably for most of the people like this. I'm not sure. So yeah, the problem that I have only my experience, and I cannot say too much about other students.
Right, but we are interested in your experience. We are interested in your experience very much. Okay, well, thank you for answering my questions. So is there anybody else with any questions or comments or suggestions or?
I have another question, if that was good. Thank you for the talk. So my question is a bit general. So these photonic circuits, are they fully tunable? And do you think that there are methods for training those circuits for purposes that potentially relates to detecting patterns or classification or state discrimination in more of a learning settings?
Yeah, it's a good question. So here, for example, you on the right side can see two different examples of it. So in the first example, what was done, it was just a static beam splitter with static interferometer with no any ability of changing the relative phase. It was fixed. Yeah, but on the second approach is already was done one step further, and there are some ways how to manipulate and change your circuitry in time, and usually it is realized through electro-optics because it's fastest what can be done, and the most efficient one. And I think about this training, what it does, you based on your answer on the output, you should slightly change your system. So I think it can be done with such kind of approach with electro-optical, and actually there are some approaches to realize it on chip based on material which is aluminum nitride, for example, is good for this. But yeah, everything is doable. I mean, people are working on it. There are some other. It's actually a huge field which is called neuromorphic quantum, not even quantum, but just neuromorphic computers, optical computers, where people specifically trying to solve this kind of problem. So and not only this, so and of course, currently it's in the stage where people try to show some scalability. But after all, of course, everyone is interested in switchable and tunable systems.
Yeah, thank you.
I have one more question.
Mm-hmm.
Can you please go back to the nitrogen vacancy slide? Yes, yes. So on the right, we see the phonon line. Is that the wavelength you're looking for, or is it a different one? Or you don't?
Yeah. So in principle, if you put a filter, you can use any of this line or any of these wavelengths. But when you go to low temperatures, this huge peak disappears, and you have only zero phonon line.
Okay.
And this is like an inherent of this two-level system. And if you want to see some more quantum effects, which are related not only to photons, but to this electronic, to this electron and the photon, like entanglement. If you want to create entanglement between electron and the photon, you have to work with the zero phonon line.
Okay. Okay. All right. Thank you.
Well, so if anybody has any other questions, We can ask them now.
I have just like a general question for everyone. So I am interested in PQC and I'm studying Kyber right now. And I'm interested in quantum currency as well. So I would just reach out, like if anyone is interested in the similar things, we could have a talk about that.
Okay,
Thank you.
that's good. This is going to be on the video, so we're going to use it. People will refer to it and come back to you. Yeah, perfect.
Yeah.
Well, so Demid, thank you so much for coming here and speaking to us tonight.
Yes.
Thank you for attention.
Yeah, we're going to stay in touch with you.
Yeah, yes, sounds good.
Thank you once again. So with this, thanks everybody and have a great end of finals week.